Good morning and good evening, everyone. Welcome to DAC, Data Colloquium Analytics. And today we have a very VIP guest here, Professor Michael Alvarez, and also we have Jacob Morrier, Doctor to be, PhD to be. This is a great honor to have them to join us today. Before we start, and then let me just briefly give me just 1 minute and then to introduce this deck to you. If this is the first time you join us, Data Analytics Colloquium is um, it's a platform, or this is a place that we established 4 years ago. Carl and I, we have this idea and try to convene all the top-notch scholars and try to share all those, mostly from the political science methodologists. Today, including today, we have the quite very interesting topics to share with everyone. So Data Analytic Colloquium is supported by National Chongqing University in Taiwan, and then also UTD, University of Texas at Dallas School of Economics, Political and Policy Sciences. We try to convene as much as possible and try to convene international scholars and data scientists in online seminars here and then the workshops. We're all, so honored and prestigious to have all those there's great scholars to share their research on this webinar. And for anyone who are interested in the previous webinars, we have a website. The address is dacolloquium.com. So you're welcome to visit. And then to save everybody's time, and let me turn the microphone to Carl. Carl can introduce our two distinguished guests for everyone. Thank you.
Hello, thank you, Peter. I'm so honored and to have the opportunity to introduce you to our great speakers, excellent speakers tonight and this morning. And let me introduce Jacob Morrier, and he's a 6-year PhD candidate, and he's basically a few months away from getting his doctoral degree. He's a candidate in social science at CalTech, California Institute of Technology. Let me check that, and if I can control the mic a little bit. Okay. All right. All right. For now, I'll mute on the mics. And he specialized in advanced quantitative methods, and including causal inference, econometrics, and machine learning. And he applies these tools to analyze administrative behavioral text data relevant to substantive questions in political economy and political science. And he has a really strong record of publications, and his paper or his work has been published in top journals like including JP and Journal of Politics, Political Science Research Methods, and Political Research Quarterly. And he currently holds a Master of Science degree from CalTech and a Bachelor of Science degree in economics from Université de Quebec and Montreal. And forgive my French. And also has a bachelor's degree in financial economics and engineering from University of Paris Dauphine. And another great speaker I must not miss was Dr. R. Michael Alvarez. He's a Linkage Foundation Professor of Political and Computational Social Science at CalTech. And he is also a co-director of the CalTech MIT Voting Technology Project. And he told me that he has been super busy because of the recent elections. And actually, I'm really interested in learning from him about the data for the 2024 elections. And currently, he is a faculty member in social sciences in CalTech, and also associated faculty member in the social and decision neuroscience program. And he recently became the founding co-director of the CalTech Center for Science, Society, and Public Policy. and he's a fellow of the Society for Political Methodology and a fellow of American Academy of Arts and Sciences. Dr. Alvarez has been recognized for mentoring works and both at CalTech and at the Graduate Student Council. He has been there twice and 2 times nominated, and also in the Society for Political Methodology. And if you happen to be in one of the POMED or any political methodology conferences, that you know his name really well, and he's particularly strong and well renowned, has a great reputation of mentoring, helping younger scholars, younger generation, younger students. And he is also a faculty liaison to CalTech's men's basketball program. And that is not as well known as his works, but he's very active in educational institutions and other nonprofit organization activities. So I wish I can have another hour to read out Michael's accolades, and also, but he's a very strong record. It's well known and to students and mentoring students, and I am really privileged. And actually, we are in both NCHU and UTD, and at the Texas Methodology Conference earlier this year, organized by Patrick, and I met with him. He mentioned a couple of new methods to the attendees, and I'm particularly interested in the record linkage method, which is one new data science methods. And not many of our programs have this in the curriculum, and I really appreciate this opportunity that our students can learn from Michael and Jacob directly about this record linkage method. And I think I used too much time. Without further ado, let me introduce our honored speakers, and Jacob and Michael. Thank you.
Well, thanks for that incredible introduction. I'm going to start for just a minute or two and set some quick context. And then, of course, I'll turn it over to Jacob, because he will run through in just beautiful detail this method that he's been working so hard on for about 2 years. So some of you who know my research know that a lot of the work I've done has focused on latent variable models, in particular in social and political science. Latent variable models have become increasingly difficult to estimate because of the size of our data sets and the usual complexity of and nonlinearity of those models. A few years ago, we started working with tensors and tensor algebra in an attempt to try to simplify the estimation of certain latent variable models, in particular in the area of natural language processing. And we've actually built some approaches to that, which I talked about at the TextMeth meeting, and some of those papers are going to start to be published relatively soon. Now, as Jacob will talk about, this problem of record linkage is a latent variable problem. And a few years ago, Jacob and I started talking about the application of tensors to this particular latent variable problem, and I was adamantly convinced that they would be the solution to the estimation problems and the computational problems that we see in the problem of record linkage. And Jacob started investigating this, and turns out that he came into my office one day. We had a very long meeting, and Jacob had to demonstrate to me that I was wrong, that tensors were not the solution to the problem. As you can imagine, that was an interesting meeting. We had a lot of fun with it. But Jacob also demonstrated during that meeting that he had another solution. And that solution was using GPUs, or graphical processing units, to try to solve some of the computational complexities of record linkage. And that's the origin of the project. I thought the context would be, in particular, a lot of fun, especially for students who are listening to the call, because sometimes you do have an opportunity to demonstrate that your professor and advisor is wrong. So with that, I'll turn it over to Jacob, and we're looking forward to getting feedback and hearing folks' questions about this approach that Jacob's been working on. Thank you.
Thank you very much, Mike, for the introduction, and thank you for your invitation. I'm just going to set up the slides, and so I think we're ready to go. So I'm also gonna mention that this is joint work, obviously, with Mike and with Suleika, who's an amazing undergrad student. I don't think she could join us. Maybe she's gonna try later on. She had a conflict, but she's also helped me, and she's helping me think about the various possible applications of that work. And so let me get started. So if you're like me, you might be, obviously you're going to listen to the presentation, but you might be impatient. So that's where we're going to end. I'm going to show you exactly what the documentation looks like, but already I'm going to extend you an invitation if you want to already go ahead and start exploring the documentation. So here, I think the main the starting point is that record linkage and deduplication are very important tools for research in social sciences. And so these tasks in general, they consist of identifying matching records or potential duplicates across data sets where we might lack consistent unique identifiers. So variables that identify uniquely each entity of interest, and also data sets where there might be errors or inconsistencies across variables that prohibit us from safely merging these data sets simply based on those variables using standard merge techniques. And so record linkage and deduplication, so these tasks, they go beyond our hard merges, and they specifically require calculating string similarity metrics for all pair of values between data sets. And although these calculations, like one comparison alone, is relatively simple, the problem here is that the number of comparisons grows exponentially with the number of observations. And the example I like to use is, imagine we're comparing two data sets that have 1 million observations each. It's not like in our day and age, it's not that much, but here you'll see that we really run very quickly into problems. So two data sets with 1 million observations each, if I'm adding one single observations to one of those data sets, it creates a million additional comparisons. So you see here that as the data sets I'm trying to compare and trying to merge, they grow, then the number of computations involved increases as well. And so that's going to make the processes of record linkage and deduplication especially computationally expensive. And so the solution that we used, as Mike mentioned, the solution we propose is to harness the computational power of GPUs, graphical processing units, to accelerate these processes dramatically. And so I'm sure you've all heard a lot about GPUs, especially in the past couple of years, where they've been extremely useful in advancing the fields of AI and machine learning. And I'm going to try, I think, in the course of the presentation, to demystify them and show exactly how they are helpful to us in our tasks. But so the bottom line here is that moving that process to GPUs allows to speed up the process by over 30 times, and sometimes even more than that. And so it has the potential here to reduce execution time. So the time it takes to do record linkage or deduplications from hours to minutes, and it greatly enhances the scalability of those methods for moderate to large size data sets. And here right away, I'm going to show you performance comparisons. So here we took voter registration data, and I'm actually going to walk you through a bit at the end of the presentation through a concrete example. But here we're just comparing execution time as a function of the size of the data sets. So here we're looking at the time it takes to merge two data sets of some, like, starting from 1,000 observations to 100,000 observations each, and compare the execution time of our package faster with the leading CPU powered software implementation FastLink. And so you see in those on those figures that we're increasing the process by, for 2 data sets of 100,000 observations each, that process is 30 times faster. And these speed improvements are even more dramatic when we consider deduplications, where if we're trying to deduplicate, so find potential duplicates in a data set of 100,000 observations, then moving to our package to faster increases execution time by 60 times. So it takes 60 times less times to do deduplication. And so the first time I actually showed those results, I had a colleague who voiced, I think, a legitimate concern here that, yeah, GPUs might indeed be faster, but in general, at least for the same computing time, they are more expensive. And so here I've done back of the envelope calculation to just show you that actually these speed improvements, they also result in cost improvements as well. So I'm considering the task of linking 2 data sets with 100,000 observations each. And so I've taken very simple machines on AWS, so cloud computing infrastructure. And so comparing what's the cost of doing that tasks on CPUs, it's a bit more than 6 cents versus GPUs, where it's about 1/3 of a cent. So here the cost of doing that linkage is more than 80 times less on GPUs than CPUs. And so later on, I think I'm going to spend quite some time talking about GPUs, what's so special about them, and why they are so good at doing record linkage. But before I do, let me just start by describing the process. What's a typical record linkage or deduplication pipeline look like? And so I'm going to try to think about these things in theory, but also show you how how it manifests concretely in our package architecture. And so here, the package, in terms of design philosophy, in a way, we try to make it. We try to make modular classes that you can customize to your needs and requirements, and you can kind of use them as modules in record linkage or deduplication pipelines. So in general, and I have great figures that kind of show you like the inputs, the outputs, and the different classes. I'm going to show you that in a minute. But so in general, we have classes that require user supplied inputs, and they produce relevant outputs, some of which you pass on to subsequent classes. So in general, and I'm going to run through each step in turn, but so either record linkage or deduplication pipeline, standard pipelines, they consist of 3 steps. The step number 1 is calculating the string similarity metrics I was telling you about earlier. And so once we've done that, we are going to pass on the results to a probabilistic model that aggregates and summarizes the information, the Fellegi-Sunter model. It's been around. We didn't come up with it. That's what FastLink uses, and it's been around since the late 1970s. So it's been tested, and I think it has proven its utility here. And so once we've estimated the Fellegi-Sunter model, we simply match all pairs that exceed some threshold. And so I'll walk you through all the steps, but kind of let me just look at, here's kind of a high overview of what this process looks like in the context of our package. So I was talking to you about the modular classes. So these modular classes are represented by the boxes here. So in general, a standard pipeline is going to consist of 3 classes. Here we're looking at what it looks like for record linkage. So we first have a comparison class that takes in 2 data frames and lists of variables according to which we're trying to join or link those data sets. The comparison class is going to compute the string similarity metrics for all pairs of observations between the 2 data sets, and is going to pass on the result to an estimation class that's going to estimate the parameters of the Fellegi-Sunter model. And afterwards, once this is done, then we have one final class that is basically just gonna take some user supplied threshold and return a linked data frame that accounts for all the information that has been estimated beforehand. And the process is very similar for deduplication, except that when we do deduplication, we only look at one data set at a time, right? We're trying to find the possible duplicates in a single data set. And so that's reflected in the inputs. And so instead, like in the previous pipeline, we replaced the comparison class with the deduplication class that basically just accounts for the fact that we can divide the number of comparisons needed by half. And so that's going to dramatically speed up the process. And I think that's reflected in the plots I was showing you earlier. So let me kind of run through all the 3 steps I was telling you about. So step number 1 is the calculation of the string similarity metrics. And so the need for those similarity metrics arises from the fact that hard merges, they are vulnerable to typos and inconsistencies. In general, you need only one single character difference to disqualify a pair from matching in a hard merge. And that's a problem. And I think that's the main problem of hard merges. And so we need a method to compare variable values that is going to be resilient and robust to these errors, potential errors and inconsistencies. And that method, it should reflect the full range of similarities between 2 possible values. And so here I'm kind of, it's a very stylized example, but so here imagine that we're trying, we have a data set, you know, that for some reason has some errors and inconsistencies. And so I'm trying to find in that data set the observation that matches me. So my first name is Jacob. And so imagine in that data set, we have one observation that says Jacob, and the other is Mike. And so here we need a string similarity metrics that I think we all have the intuition that Jacob is probably closer to Jacob than Mike is to Jacob. And so we need, and that's what the string similarity metrics do. They basically are able to account for the fact that Jacob is closer to Jacob than Mike is. And so although there's kind of a full spectrum, a full range, a continuum of similarities between 2 values, in general here, because mostly for, I think, memory constraints reason, we're going to discretize similarity levels. So usually we put like each pair of observations in one of 3 buckets. So the one would be, you know, like pairs that are completely different. For instance, Mike and Jacob would probably fall in that category, right? They have no letters in common. They're so different, so they would fall in that bucket of completely different pairs. On the other end of the spectrum, then you'd have you know, the bucket of identical or close to identical values. Jacob would probably fall in that bucket. And in between, we're going to have the bucket of all the pairs of observations that are that have an intermediate similarity. So maybe if we were changing more letters to Jacob, so if it was Jabov, for instance, then maybe it would fall into that intermediate bucket. And so really, I want to emphasize that these string similarity metrics are really the distinctive feature of regular linkage and deduplication, but they are also the primary bottleneck in that process. And so here, let me mention that there are multiple string similarity metrics available in the market. I've only put basically 3 or 4 of them, but if you go online and start reading, you know, there are hundreds available in the market. But I think I just want to discuss 3 of them. So the first one is, I think, the simplest, and it's the Jaccard similarity. And so here, those of you who are familiar with NLP are gonna I've certainly heard of the bag of word approach. And here, in a way, it's a bag of letter approach. So we're simply comparing the number of common letters between 2 strings, independently of their order. And so it's very simple, but also very naive, right? And on the other end of the spectrum, if I may say so, we have the Levenshtein similarity, which is, I think, the most comprehensive metric, in the sense that it's trying to account for all the differences between 2 strings by counting the number of changes you need to go from one string to the other. And here in the package, and I think it's relatively common, and I think it's a standard, we use the Jaro-Winkler similarity, which I think is a compromise between kind of the two approach. So it's not as comprehensive and complicated than the Levenshtein similarity. So there are a number of underlying assumptions, but it's still kind of accounting for the order, for instance, of the letters occur in a string. And so here, the Jaro similarity is basically measuring the share of matching characters that occur in the same vicinity in 2 strings, and penalizes transposition. So when letters, although they might occur in the same vicinity, they aren't occurring in the right order. And the Jaro-Winkler similarity is simply a twist to this Jaro similarity that puts an extra weight on the shared prefix of strings. So it rewards the fact that 2 strings would start with the same letters. So those are the kind of very common string similarity metrics that are being used. And so, as I was telling you, that although for given pair, so you give me 2 strings, computing these metrics is relatively simple. The problem here is really that the number of comparisons increases exponentially with the number of observations. And so, like I put again the example I gave you earlier. So imagine our task is to compare 2 data sets with 100 million observations each. It's like I said, in this day and age, those are moderate sized data sets. And adding just a single observations to either data sets results in 100 million, not 100 million, but 1 million additional comparisons. So imagine now if you were dealing with 2 data sets that add 10 million observations each. Then you see that the number of observations is really going to grow quickly, and that's going to be a problem and a challenge for us. And so one solution, a very simple solution, that's one that has been kind of used before, is to limit these comparisons to unique comparisons. And so the way I would explain this is, imagine I'm trying to compare first names. In any given data set, first names are going to occur multiple times, right? So if I account for the fact that there might be multiple people in my data set that are called Mike, I can reduce the number of comparisons that need to be made. And so here that plot is basically showing you I took North Carolina voter registration data and I did some random sampling on it to build like data sets. But so here, if we're just accounting for the fact that first names can occur multiple times in a data set, we can dramatically decrease the number of comparisons to be made. So here for first names, it would be 6 times. So we're able to divide the number of comparisons needed by 6. And so for last names, it's even more. It's close to 15 times. Even when we account for that, we're still faced with the fact that, and it's meant to illustrate this, that we're still faced with the fact that the number of comparisons, and you clearly see it in those plots, grows exponentially with the size of the data sets. So that's really kind of the computational problem. And here what our package does is doing all of this on GPUs. And that's really, I think, not surprisingly, it's the lengthiest part of the process. And that's also where the most significant performance gains are achieved. And I'm going to discuss, later on, I'm going to be very specific about what is so special about this task and GPUs that we can achieve those performance gains and these improvements. But so before I do, I'm going to finish describing kind of the 3 steps of the record linkage and deduplication processes. And so you'll remember that in these 3 steps, so step number 1 was calculating all these string similarity metrics. And so the second step is to estimate the Fellegi-Sunter model. And so the need for that is that, so if you think about hard merges, they are going to be looking for exact matches across all variables. But in practice, that might not be the case, right? A match might have a discrepancy or over one variable. So the example I'm thinking of is you might be linking 2 data sets and someone, has changed their phone number, right? So you need to be able to kind of allow for the fact that maybe phone number doesn't match, but the rest matches. So maybe that pair constitutes a match, right? And so that's another vulnerability of hard merges. And here the value of the Fellegi-Sunter model is it allows to combine and synthesize the information from multiple variables. So we're going to be looking at the information from the similarity over first name, last name, address, phone number. And so we're combining all this information to define an optimal decision rule, to set like a threshold here, and to decide which pairs we decide to link and which pairs we try to leave unmatched. And so the Fellegi-Sunter model, it's the term that is used in probabilistic record linkage and deduplication, but it turns out that it's actually a very common latent variable model that is used in a wide variety of setting. We call that a naive. You might have heard of it as a naive Bayes model or a naive Bayes classifier. And so the main input of that model is the discrete levels of similarities that are implied by the string similarity metrics. So what we do for every single pair of observations, we define what we call an agreement vector. So that agreement vector, each of its elements is going to contain a discrete level of similarity over one variable. So for instance, the first element of our agreement vector could be the discrete similarity level for first name, for instance. And so that's the main input. And so that comes directly from step number 1. And the model presumes the existence of a latent variable. And that latent variable is just encoding whether, for each pair, whether that pair constitutes a match or not, a pair of observations. And the model follows a simple finite structure. So we assume that the latent variable is distributed Bernoulli with probability lambda. So that means that there's so if we're taking a given, like a random pair of observations between two data sets, they have a probability lambda of constituting a match. And the second kind of component is the distribution over discrete levels of similarity, conditional on match. So here we have these vector pies that basically tell us conditional on match for on match status. So whether the pair is a match or not a match. For some variable, we have a probability of having a low, medium, or high similarity. And so when we put all these things together with Bayes' rule, the model yields estimates of the conditional probability that each pair constitutes a match. And that's the information that we're using for step number 3, which is very simple, is we have for each pair a conditional probability that that pair is a match. And so we set a threshold, and we merge all the pairs that are above that threshold. Before I move on to like talking to you about GPUs, the parameters of the Fellegi-Sunter model are estimated with I'm sure you've heard all about it, the expectation maximization or EM algorithm. And I just want to talk about like what the underlying assumptions of that algorithm. And so here the algorithm operates under 2 assumptions. So the first one, you might have an idea by now. So we group the observation pairs into 2 clusters. So the first one being the matches and the non-matches. So we have kind of these 2 buckets, and we're trying to put all the pairs in either of those buckets. Or we want to get a sense of how likely it is that each pair falls in each bucket. And here we're just making this, I think, reasonable assumption that matching pairs tend in general to exhibit a higher level of similarity across most columns than non-matching pairs. And so the EM algorithm just iterates and finds the optimal decision rule that allows us to best distinguish between these 2 clusters. And in general, it does that in an unsupervised fashion. So there's no need here for labeled data. Although I think it's relatively common. I'm saying that, but there's a caveat that I think it's relatively common to, at least for a small amount of observations pair, to do some labeling. In that information, that those labels can allow us to refine the decision boundary. Right. So I think that's the end of the description of the record linkage and deduplication process. I'm just trying to give you like a high-level overview. And here there's nothing, that's not where our contribution lies. It's really, our contribution is really to move that to GPUs. And so I want to spend, yes, Carl, please.
Oh, great. Hey, thank you, Jacob. This is really, really, really interesting. I want to pose maybe 1 to 2 questions, and could be Mike can weigh in here too. So when when we talk about record linkage, we want to merge data sets, multiple data sets, and a few challenges of this merging enterprise. And number 1, we do not have any unique identifiers. So for example, this is a survey. done in a U.S. population and with certain sampling method. And okay, so I think that will be coming to some latent variables, and that Mike can weigh in later. And then the second data set is tapping in the same population, similar or maybe comparable or even identical sampling methods. So that will be giving two data sets or multiple data sets coming out of the same population. So we want to merge this. And there are couple challenges. One is, how do we know the individual respondents have responded to similar to different surveys? Then we can identify them. Oh, this is John Doe answering survey 1 and John Doe answering survey 2. So then we can find ways to using recurrence methods to identify this and merge this data. So that is one scenario. I want both either one of you to give us some shed some light on that, and how we can use the recurrent linkage to merge this data set to basically tap into the multiple data set that's still being unused until they are merged. And did I ask the question clearly?
Yes.
Mike and Jacob? Yeah. So
yes,
using go ahead.
Yeah. So I think the example you gave is a great one, and so I intend to finish the presentation showing you like a fully worked out example. So I think it's going to give you an idea of like the capabilities and where that model can be useful. But I think the example you gave is a good one. If you allow me, maybe
Sure.
to kind of so here the record linkage and deduplication are going to allow us to do these merges. So for instance, imagine you have two data sets like you said, and imagine survey data. We were collecting first names and last names just to stay very simple. But the challenge, and I'm gonna use Mike as an example, that Mike sometimes he might when asked his first name, he might just write Mike, or he might write Michael, or he might write R Michael, right? So that's really what the challenge or the problem that record linkage and deduplication are trying to address, right, and circumvent in a sense. Hopefully that is. I don't know if Mike, you want to add anything here, but hopefully that makes it a bit clearer.
I guess the question I'd have, Carl, is: are you talking about situations where you'd actually do have some identifying information, like Jacob said, or whether these are like data sets that you'd get from the ANAS or CCES, where there's no identifying information at all?
I think the process of de-identifying the data is a lane process, and it could be, for example, now it's not just simple anonymizing the data, but you still can use, for example, some more data for matching, such as residential data. I mean, the vague one, and maybe North County, and sometimes your blogs, and then you can use other information like gender, and then to help, just like from a database perspective, it's like putting together like a super key. So this use multiple variables to use the super key to reverse the process of anonymization, and then try to identify these records or combine these records. So record linkage method, I think I really look forward to see more slides, because I think Jacob is using another example. But that is the second question is a little bit more difficult to express. For example, some variables are meant to change, and because, for example, you want to combine the surveys for from different time points, even though from the same population. So that variable did change because it's a process. Is that some variables will not change? For example, gender, and now for now it's still a variable, and I understand that gender could be different. But now generally some variables should not change, and last name, for example, maybe gender and maybe the state, and so then the process of selecting these variables, how much these variables can contribute to that super key combination. So that could be a challenge and difficult, and some variables are meant to change, and some variables are meant to stay in the same, and all throughout. So that is something maybe Jacob can illustrate with an example, and how much we can use this method to get better merging and with this super key concepts. And yeah, I think I have another question from and no, I think we distract too much.
No, but very briefly, I think you're raising an interesting point. So I would emphasize here that there's a lot of domain knowledge that's needed here. So like as analysts and as researchers, I think we need to go through the process you were talking about of thinking, well, what are the variables that are meant to change and those that aren't meant to change? Because sometimes if we're trying to merge according to some variable that is just completely unreliable, then we're just creating an obstacle for ourselves, right? So I think we need to exercise judgment in that sense. But I would also emphasize that the EM algorithm, the Fellegi-Sunter model, kind of attributes different weights to the variables in a sense. And so it kind of can account for the fact that maybe some variables tend to change a bit more than others. So for instance, probably last name is not, well, you're gonna have people, for instance, who marry and change last names, but it's probably fixed. And maybe the model could do the same thing for gender, right? That's something that, although you're gonna have some situations where it change, for the vast majority of people throughout their lifetime, it's not gonna change, and that's probably something where you don't have a lot of typos or inconsistencies either.
I think we may have distracted digressed too much. Do you still want to entertain one more question from Glenn?
And then afterwards I can move on to GPUs.
Glenn, go ahead, please. Glenn, hi. We still cannot hear you. I saw your mic is unmuted already. All right, and but maybe I can read out Glenn's question.
It's in the chat.
Okay. I understand your focus, and I do have a clarifying question. Are the pairs a set of variables, or also possibly a pair of records? Oh, record. Okay. So that is columns or rows?
Rows. So yes, that's an excellent question. Thank you for asking that question. So when we talk about a pair, so we're considering 2 rows, 1 in each data set, or like if we were doing deduplication, that would be 2 different rows in the same data set. Thank you for that question. Thank you.
Okay.
So now let me relatively quickly just go through GPUs, and I want very briefly to discuss, because I think we've talked a lot about them these days, but I feel like for most people it still kind of remains a mystery. And I also want to discuss, well, what's so special about GPUs that make them highly suitable for record linkage. And so here, if we compare GPUs with CPUs or central processing units, which you have in all your computers and is really the brain of your computer, they have very different design philosophies. So in a nutshell, CPUs, they usually have few powerful cores with a lot of cache memory, whereas GPUs are going to have hundreds of smaller cores that are capable of executing thousands of threads at once. And so what it does is that CPUs and GPUs at the end of the day have different strengths and are good at different tasks. So the idea behind CPUs is to achieve speed. So you want to take one set of instruction, one thread, and you want to execute it as fast as possible. Whereas for GPUs, if we take one single thread of instructions, that thread might take longer to execute, but we're really trying to achieve throughput or volume here. So maybe one single thread is going to take longer, but we're able to run 1,000 at a time. So at the end of the day, for certain tasks, and I'm going to be very specific, we can gain in volume and achieve better performance in that sense. And so I'm not an electrical engineer, so I'm not going to get into the details, but you can think about CPUs and GPUs as having the same fundamental ingredients or components, but that are arranged or distributed in very different proportions. So I'm just going to be kind of more specific. I think I gave you the intuition, but so GPUs are optimized for what we call data parallel tasks. And these tasks, and there are countless tasks like that. And that's why people love GPUs and they are becoming so popular. But these tasks, they basically involve executing the same operations or the same instructions independently across multiple data points. And that's reflected in the GPU programming models that are really designed to enable data parallelism. And just to be kind of introduce a piece of terminology here. So data parallel operations are defined in what we call kernels, which are analogous. You can think about those as the instructions in the body of a for loop, right? So one way to do, an operation over multiple data points would be to program a for loop. You can think about the kernel as being what's inside that for loop. And so here, I think that's the textbook example of a data parallel task. And so I made a figure to show you. So vector addition is, like I said, a textbook example of data parallel task. We're trying to add two vectors, vector A and vector B, to obtain a vector C, which is going to contain, each element is going to represent the sum of the elements, the corresponding elements of vector A and B. And so I think my hope is you can see quite clearly that the vector addition can be broken down in many, many smaller independent calculations. So we can break down the addition of the vectors A and B in simply additions of corresponding elements of vectors A and vector B to obtain each element of vector C. So that's once again, the textbook example of a data parallel task. And here I have a figure trying to convince you that calculating string similarity metrics is also a data parallel task. And that's why here we're able to harness GPUs. So here I have basically a matrix, what is meant to look like a matrix. And so you can think about each column representing a row or record in data set A, and each column, yes, and each row representing a record, an observation, or a row in data set B. And so we're trying to fill that matrix. And so here, each element can be computed independently of the other because it involves comparing a different pair of observations. So the similarity between row 0 of dataset B and row 0 of dataset A is independent of the similarity between record 1 of dataset A and record 0 of dataset B. And so really that's also a data parallel task. And again, that's why we're able here to harness the computational power of GPUs and to do so so efficiently, so effectively, yeah. And here I'm gonna do just 30 seconds of publicity, not for me, but so for the authors of this great package. I'm sure some of you might have heard about it, might be familiar with it, but CuPy in Python. And so so those who are already familiar with programming in Python, you can think about this as the GPU accelerated equivalent of NumPy. And really the authors of that excellent package really tried to closely mirror the API to that of NumPy. So that package is gonna contain a number of standard routines, standard operations that we use in array-based numerical computations, but it also allows us to define custom kernels again. So think about these data parallel operations, right? That the inside of the for loop body. And so these kernels, they must be written in this special programming language called CUDA. You might have, I'm sure many of you have heard at least the term before. And so it's essentially a C++ dialect. So it's based on C++ with sometimes minor differences. And so CuPy, I think they've done a very good job at building what I call templates. So just wrappers that allow to do very common, well, that are based on very common patterns observed in data parallel tasks. But the thing I want to show you is also allows you to just define free-form kernels. And so I wanted to show you a bit what it looks like. I don't know if it looks intimidating or not. It was intimidating for me when I started. It no longer is. But so essentially here, what I'd like to point out, it really looks like the inside of a for loop body here, because you see that. So that's the a kernel for vector addition, and you see that in that vector, we've basically just isolated the addition of 2 specific elements of our input vectors. So just trying to make a link with what I was showing you earlier. And so when I launch a kernel, CUDA is gonna execute that instruction 1,000 times on different data points. So it's very powerful. I just want to take a minute to discuss maybe because I think with CuPy and certainly with the technology that we have today, it's never been easier to do CUDA and GPU programming, but there are still challenges involved, especially someone coming from R or Python. C and C++ are low-level language, so they're not going to have as many high-level abstractions. I think a challenge, a big one, is debugging. So and that's the corollary of the computational power of GPUs. That every time you launch something, you're launching thousands of operations at a time. So when something goes wrong, it's difficult to go back and see exactly where it went wrong, because you're basically at any given time, you're doing 1,000 calculations at a time. So you need to figure out among the 1,000 things you've done, what was wrong. So that's a challenge. Another one, because R and Python are very forgiving in terms of memory management. A lot of it is done for you in the background, whereas with CUDA and C and C++, you need to do a lot of these things on your own. And so that requires becoming familiar with explicit memory allocation. You need to account for data transfer overheads, because that's an important detail, that discrete GPUs like CUDA-enabled GPUs are going to have a different memory from the CPU. So in general, you're going to be programming on the CPU and using the memory of your CPU. But the moment you want to do an operation on GPUs, you need to move the data to the GPU memory, and once you're done, you need to move it back to the CPU. And so that there's some non-compressible amount of time involved with that. And another point might be a subtle one, but actually, the moment you start programming, turns out that although it's subtle, it's very important. It's dynamic memory allocation. So it's very expensive for you to, in your kernels, to do dynamic memory allocation. And so an example of that is, so you're trying to, for instance, you want to create a vector whose size might depend on the size of your inputs. And so in general, that's very costly to do. And so it can eat basically all your speed improvements from moving to the GPU. And so one way to circumvent that is to allocate working memory before you start the operations. But one challenge that I want to talk about, because it's a big one, at least for our tasks, is the fact that GPUs do not natively support jagged arrays. So jagged arrays are basically arrays of arrays where the inner arrays can have different lengths. And here, an example of that would be an array of strings. So strings, usually you see them concatenated together, but in fact, for the computer, that's an array of single characters, right? So my name, Jacob, I see it as something contiguous, but for the computer, it's just an array with J in the first element, A in the second element, etc. And so that means that basically it's very difficult to store strings on GPUs. So you can imagine it's a big problem for us, because all we do is work with strings. But turns out that there's actually a simple solution that it is becoming, I think, widespread in a lot of packages that are popular or becoming popular, use that in the background, is the arrow columnar format. And so if you think, and the next slide is basically showing you an example of that. But so this approach basically consists of storing a jagged array in two different elements. So the first one would be the primitive layout. So imagine I have an array. I'm going to go right away to the example to make that very concrete for you. So imagine I have an array of first names. I took very common American or English first names. So I have this array of strings, can store it on GPUs like that. What I do is I convert it in an array of single characters. So I just break down the first names in their characters. And so that's called a primitive layout. And next to that, I store what we call a sequence of buffers, for lack of a better word, that simply indicates in that big primitive layout where each of the first names start. So for instance, David starts at position 0, Elizabeth starts at index 5, etc. And so the moment we just change our way of thinking about arrays of strings, and we think about those as in the arrow columnar format, then we're enabling, empowering a lot of stuff. And so now, as promised, and that's almost the last thing, I want to talk to you about. I want to show you an example. And so here what I've done is I've constructed two artificial extracts of North Carolina voter registration data. That's publicly available. So I have constructed two data sets with 100,000 observations each. And I made sure that in these two data sets, we have 50% overlapping observations. So this 50% of the data sets are basically the same voters. And 50% in each data set is just different voters. And we're going to be merging observations in both data sets by looking at first name, last name, house number, street names, and birth years. And but what we do and the twists, and that's meant to kind of replicate the kind of environment we might face is, that something like these two data sets that I've artificially constructed, they might have come from two different sources, and they might not have been managed in the same way, right? There might be inconsistencies. There might have been errors and typos, like humans are prone to errors. And so as you were typing the data in, you type the wrong character. And so we do for 5% of the records, we do a set of operations. So we add random characters, we delete random characters, we randomly shuffle two contiguous characters, we replace a character with another, we also shuffle records. So sometimes we take someone's first name and we put it, we replace it with someone else's first name, and we do the same thing. So really shuffling. And so we'll see that in that situation, hard merges fail. And our approach, the Fellegi-Sunter approach, is both fast and so here I'm really hoping there's just going to be a few seconds to get started, and I'll show you that it's both fast and very precise. So right away I'll be able to show you what these data sets look like. So we see here we have two data sets that we can already, if we just look at the first couple of observations, we're going to see that some of them are basically the same, and sometimes we see that there are different ones. And so here I'm confirming that there are 50,000 here, because I've artificially constructed these data sets. I know I know who the common voters are, and so here I'm confirming that I have 50,000 common voters, and so here it took 32 seconds. And so if I were to so that's kind of a caveat that's worth mentioning. So every time I'm doing, so imagine I'm starting my work day and I'm merging two data sets. The first time there's going to be a small overhead of 5 to 6 seconds just to compile everything. But so if I were to, and I'll do it just for the sake of showing you that that if I were to run it again, I'm going to gain 5 or 6 seconds. But here, what I really want to show you is to compare the results between a hard merge. So if I basically were to merge both data sets on those variables without accounting for the fact that there might be errors, inconsistencies, etc. So maybe the redeeming quality of hard merges is you tend not to do a lot of false positives, right? Because it's so stringent. So all the observations that we do indeed match are indeed matches, but we're actually doing a very poor job at recovering matching voters, right? Because there are errors and inconsistencies, and so all these errors and typos they disqualify potential matches. So we only recover 36.5% of actual matches. Whereas with the probabilistic record linkage method, we're still very precise. 98% of matches are that of records that we do match are indeed matches, but we make a tremendous improvement in recall, and so we're able to recover essentially all the matching voters in the two data sets. So we have a recall of 99.8%. And so here, let me show you. So it took overall that process 24.6 seconds. For the number of comparisons that you need to make, it's extremely fast. And by comparison, that same process on FastLink would have taken about 14 minutes plus, a couple of seconds. So it's really, I think, a dramatic improvement. And so hopefully now record linkage and deduplication should be more concrete for you. And really the last thing I want to do is just to point out that we have documentation online. So you can visit it, explore the documentation, and start using the package right now, and you can explore a bit. I think we've put in a lot of efforts to write documentation that is as clear as possible. But obviously, we would love it if you had feedbacks and you thought that things needed to be added or anything. But I'm going to encourage you in conclusion to explore documentation and please use our methods and right. I think that's all I wanted to say. I'd be happy to answer questions.
Quick question. I think, Jacob, is it okay you provide that documentation link to us? Do you have access to the checkbox?
Yes.
Oh yeah.
So I'll share the link with you. So it should be easy. Excellent idea.
Yeah, and I think I share with. Is it okay I share a GitHub?
Yeah, absolutely.
And
so
cool.
you
So
see that
me the GitHub.
on the homepage. So you have a link to the GitHub repo.
Yeah. Okay.
So if you go in the documentation, you can also access the GitHub repo. You can it's on the Python package index, so you can install it directly from there. And also that's a note Mike would want me to point out. So maybe some of you don't have a CUDA-enabled GPU on your computer, but actually you've seen that you're able to use Google Colab. So for every week you get about 10 hours of free GPU time. And so you've seen that it was incredibly powerful with Google Colab. And in fact, I think the package was kind of optimized for Google Colab as well. So that's another great option. I don't know as a PhD student, I use it a lot. So if there are some PhD students on the call and you don't use Google Colab, please learn all about it. It's extremely useful.
Yeah. Actually, yeah, I did. I have my student use Colab also, and if they do the Python part, but now I want to start with some very simple ones in RStudio, and because it can accommodate both and swap between both languages. They're very, very exciting, and I have lots of questions, of course. Now, allow me to check with the audience first, particularly the Taiwan side. Peter, let me see if I can. All right, good. All right, and maybe I can invite our guest in Taiwan first, And I know that you guys are about to catch lunch. I hope. I think I have a lot of appetite for this. I mean, academically, but I let the Taiwan side ask the questions first. Peter, do you have any questions from your audience and yourself? Please unmute yourself. Can you unmute yourself? I still cannot hear you yet.
And what about now?
Yeah,
Can you hear me?
yeah, it works now.
Got it.
Good.
Yeah.
Got it.
All right. All right. So I'm in a classroom setting with my students here. So we have two sets of computers. I have my laptop, and then there is another computer. So I'm kind of jiggling between these two. All right. Back to the questions. I have a couple, but before it goes on, I have to let you know that not all of our audience today come with a strong data engineering background. So please bear with us. If the following questions need to be better, organized to hit the very core of what you presented here. And the first one, I think, is quite quick one. A quick question is the matter ready to be extended to different languages, for example, like Chinese, and this is English, and as long as the structure is defined, maybe it can be extended to different languages. Well, so that's the first question. And then can I have another one? Oh,
Yeah, please go ahead, please.
here, the second question. The second question goes like this. In your experiments, how much previous knowledge is factored in when the pairing data sets are chosen? I think it's like, how does it perform for non-structured data? I know this is kind of out of the context, because we kind of match two sets of data sets. But have you ever tried to combine or to match data, and then I think that's kind of imagine that if we use this to in the context of non-structured data, and how does it perform? I mean, it's just out of curiosity. All right, so let's go with these two questions first. Thank you.
Yeah, so answer to your first question. So I think these methods have been, I think, developed with the latent alphabet in mind. And in general, I would point out that's true in NLP as well, that I think most of research is focused on English. And the moment you move away from English, like somehow, like very quickly, our understanding of methods and how they perform is much blurrier. But I think that from at least a technical point of view, an encoding, like as long as there's an alphabet at least. So I think maybe for Chinese, my knowledge of Chinese is 0, but for alphabet languages, I think it shouldn't pose a problem from at least a technical point of view. But I think that it's an invitation. Maybe if some of the students want to maybe think about like what are the problems of doing record linkage with Chinese specifically, I think there's definitely a need for a better understanding. So that's answer to point number 1. And point number 2 is I would actually point out that Mike has a paper with former students of his, Silva Kim, where they were using these methods to link voter registration data. It's been published in American Politics Research. And with Suleika, so our undergrad students were basically doing a repeat of that with 2024 data. So that's what we're working on currently. But maybe if you wanted kind of like an example, a fully worked out like paper using those methods, I would definitely recommend Mike and Sylvia's paper.
A real world example with complicated details.
Let me look it up.
Hi. This is Glenn. I just posted that question. Can you guys hear me now?
Yeah.
Yep.
Yes,
Oh,
Glenn, go
excellent.
ahead.
I had a little thing on my computer. I didn't hit the right radical button. I thought the examples, really helped out, but I'm really struggling with, okay, where do I use this in kind of real life? And that's be interesting.
Well, I think I understand. Let me give you another example. So I think why it might be so intimidating in a sense is because it's a very powerful approach that you can apply in a lot of settings. So we gave the example of voter registration data, right? So trying to find duplicates. So election officials do their due diligence. They're going to try to find maybe duplicates. And one way a duplicate might enter voter rolls is because someone changed their address or they changed their last name, things like that. Another example, so I was working at an economic consulting firm last summer, and so they were using those methods, those exact methods, to link insurance claims. So they're facing the same problem that sometimes people don't. I was giving the example of Mike and Michael. Some people aren't usually very good at being consistent. So sometimes when they have to fill out a form and they put their first name, they write Mike. Sometimes they write Michael, and so that's kind of a big problem with linking insurance claims to
Any
the same. Yeah, go ahead.
any like fraud investigation, that kind of thing?
Yeah, exactly. So I'll jump in on that one, Glenn. So part of the reason for using these in the context of voter registration files specifically is to try to look for inaccuracies, errors, and potential fraudulent registrations. Okay, so that's really the application that we have in mind. But as Jacob just alluded to, in social science, we don't really make a lot of use of administrative data. And part of it is because the simple administrative data sets we typically get are relatively thin. They're long, they have lots of observations, but they don't have a lot of variables, a lot of columns. What these methods can do is help us broaden out those administrative data sets to add columns, add features, add outcomes, add covariates to those kind of data sets that can do things like, have us better understand, for example, candidate contributions, right? Those are data sets that are administrative where we have, people give different versions of their names, the addresses are incorrect, so going through the FEC data in the US and linking it to, say, state campaign contributions data, these methods would be incredibly helpful for that. And very few people have done that. And I think those kind of data exist in other countries as well. But yeah, fraud is another application for these kind of techniques. In the private sector, as Jacob already alluded to, this kind of technique is called entity resolution. And it's used to ferret out credit card fraud, financial fraud. It's used in the national security area to try to find terrorists, to try to find criminals. All sorts of applications like this exist for these kind of techniques outside of social science. So again, students who are learning these kind of techniques, there's a lot of uses for these. If you want to go work as a data scientist, say, in the financial services industry to look for fraud, or you want to go work for the government, and use these kind of techniques to link all sorts of data sets, ranging from cell phone mobility data sets to identifying information and passport data, all sorts of applications that, again, governments all across the world are using right now for entity resolution purposes.
Yes, excellent. I actually, in a former life, I was an auditor, and I was just thinking we used to audit accounts payable, and I was thinking that this could be a very powerful tool there.
Exactly. Where you're linking somewhat disparate data sets like credit histories with other kinds of financial transactions where the identifiers, there's no identifier, but there's somewhat similar information across the data sets. Especially where it's a multidimensional problem where you're, say, using 5 or 6 different data sets, and you want to try to use that to resolve the identity of the individuals across all those data sets, we can now do it really fast across very large multidimensional data sets with this technique.
All right. This is a great conversation, and thank you, Glenn, for the question. May I ask if any more questions on Taiwan side? And I actually have multiple questions I want to ask. I do not want to take advantage too much. And do you have any questions from Taiwan side first, Peter, before I take advantage?
Go ahead.
Okay, thank you for the blessing. Now, I think earlier, I suggested that scenario, for example, some data sets intentionally anonymized. So there are methods, for example, using machine learning method to identify some better identifying variables, such as, for example, gender, such as age, such as former residents or current residents. So these are variables where you can use machine learning methods to identify some kind of super key and to vaguely identify a case. Since we do not have the last name, do not have the first name, we don't have any FERPA or personal information, and because all the surveys, a lot of research projects intentionally hide those labels, and which is in your case like names to identify these cases. So can we extend this method to use or combine with machine learning to use multiple variables to create a super key to identify these cases? Such as now, for example, we have maybe an address that is only like a street name, and we can have gender, we can have maybe age. So just name a few. So you can use this and to perform probabilistic record linkage.
Yes, so in general, you need some identifying information, right? So fully, like, would be possible from fully anonymous. No, at least these approaches wouldn't be suitable if we had fully anonymized. But
yeah,
we can account for missing data. So for instance, we don't have the first name, for instance. That's something the approach can account, right? That's another way through which our memory or database management can go wrong, right? So sometimes we lose data, but data hasn't been collected. So you can either, I think one possible assumption is just assuming that if a variable is missing, you assume it's not a match with anything, or you can create, you have in the original FastLink paper, if you really want to read through it, they propose a method to kind of account for missing data in a slightly more parsimonious way. I think especially if you have a lot of records, I think probably the results are similar between these two approaches, but it's definitely something you can account for in that approach.
I'd also say that I think that's a slightly different problem than what we have in mind here. Although I think these techniques, the GPU technique could be used to speed up the what used to be called the development of a synthetic panel. It's not synthetic panel ideas that have gotten complicated these days because people are using those to talk about AI generated data as well. But back in the day, when you would have two cross sections, right, that didn't have any unique identifiers, and you would basically want to put those together into a synthetic panel. And the technology I think that you'd use there is matching, and that's what people have typically done. if you had a very large set of data sets, these techniques, the GPU techniques, could speed that up somewhat. We've not looked into that. But I would say, Carl, just ethically, just for the students in the room, re-identifying data is not something we typically want to do. They're de-identified for a purpose. I don't want to confront you too much on this, but let's be careful about talking about re-identifying anonymized data sets.
No, I'm sorry. I miscommunicated. So because what I'm interested is not that individual voter, for example. I'm interested in that profile that represent that kind of voters. All right. So for example, I have a voter living in Iowa and age maybe 35 and male and white and I'm not interested in identifying where he lives in, what his name is, but and imagine that for example we have multiple surveys and that could be tapping into this photo, this profile, and identifying that profile or portfolio of voting records. So this is something I'm interested in, instead of interested in finding out what this exactly voted, what exactly voted for this 2024 elections. So that will be something I think it's close, very close to the idea about your synthetic profile or agent. You can call it agent, and then try to combine these multiple data sets, for example, 1 decade of data, to see how this profile changes over time. So that will be something more interesting, because we have tons of data out there. But I think you mentioned, I think you actually mentioned in the conference, we barely take advantage of this, because the individual investments are put in there. But how much we can really merge these panels, and I think you mentioned about synthetic panels, and but more I think more rewarding would be something more promising, with something we can and I want to see how this individual profile changes over time. So that I think if we leverage Jacob's method and think about GPUs, and now in the past it is almost impossible to do this, and looks like this is a possibility. We can use this technology to do that. Yeah. Yeah. And Clayton, you have a question and maybe your comments, and so I want to ask Mike a little bit more.
Yes, I know. I just wanted to make a quick comment on your first framing of your question and Dr. Alvarez's response to it. I was having this political thriller going through my head, a plot of a political thriller, because that's how the thing can be used, right? Yeah. And you know, I know the Dr. Ho, that you haven't got to my data section that I just sent out the other day on dissertation, but the Census Bureau, this is a huge thing with the Census Bureau, being able to reverse engineer from the data to identify, you know, personal identifying information, PII, to the individual by using the low-level data. So yeah, interesting.
Yeah. All right. And do we have more questions from the audience side? Let's see, our chat box. Yeah. So I have some technical questions for Jacob and Mike. And I think your paper you post on the GitHub is on Journal Open Source Software, right? So is this citable yet? Is it?
Well, so the paper is we're hoping to be under review soon. So I wouldn't necessarily cite the paper yet, but please do cite the GitHub repo and the documentation as well. We'll promote the paper. Well, fingers crossed, once it's published.
Okay. Look forward to reading the published version, and this is great work. It's great work. Um, um, I think now, I think I still have many questions. But first thing first, and Mike, you mentioned that you are working on a project and still working on the 2024 data. And can you give let us take a peek and what maybe we can invite you again for talking about 2024 elections.
Right now, you want to just like I'm still trying to just I'm trying to just digest everything that happened. But what we're doing, so the part of the project that I think Jacob mentioned that Julika is actually working on is that what we do with these kind of tools is we work directly with election officials, especially in larger jurisdictions like Orange County, California, Los Angeles County, the state of California, big states, right? Where they give us their voter registration files, and we actually use these kind of techniques in those large data sets to look for duplicate records, but to also, going back to, I think, something Glenn may have raised earlier, to take the data sets from day to day and look for changes in the records. Because if you see changes in the records that are occurring in either anomalous rates or in odd places, that could indicate attempts to disenfranchise voters or add new voters to the file or various kinds of manipulations of the data sets. So that's ongoing work. We have been working on that in particular with the Orange County data. Julika's been working on that, and we expect to have some results that we have to show the Orange County registrar first before we can publicly kind of unveil those. Now, the other work that we were doing in 2020, just FYI, had a lot more to do. Really wasn't on this front. It was much more about misinformation. We actually have a study. I can share it later, Carl. You could distribute it to the folks who are interested. But we were doing quite a bit of work in 2020, trying to figure out how to use AI to develop kind of a rapid response pre-bunking of election rumors and election misinformation. And we did some pretty cool stuff. We've got one paper that's out now. We've got a second paper that we actually built a AI chatbot that basically was developing arguments that were fine-tuned to individual subjects to try to pre-bunk them from thanks, Jacob, from being susceptible to election rumors that were coming up. So that was really what became the focus of much of our work in 2024, just because that was the big issue in this election cycle. Yeah. So the election integrity work was kind of two-pronged in this election. One was working on the voter registration files, which is the work we were just talking about. The other was the misinformation side.
Wow, exciting. Super exciting. I think, so this is something, allow me to follow up with you in future, and we're eager to send another invitation. I think that could be another conference, or could be on the same colloquium. We do it every year, but usually do it in the fall. And I think students from both sides are super interested, and I think in 2020 elections too. And the misinformation paper will be particularly interesting to students. And okay, now I know some of the authors. All right, then. So do we have any questions also from the Taiwan side? I didn't want to dominate and take an advantage. Yeah. And you unmute yourself, and Peter.
But I'm afraid I'm gonna make some loop. Okay. Here we go.
Okay, it works.
You can hear me now, right? Okay.
Yeah.
Well, just not a question, but some of our students are really interested in how this. I mean, because it's quite time efficient, right? Quite time efficient. So, do you mind sharing some research ideas about this time efficiency feature can be applied to some studies, right? Before it takes a lot of times. For example, Michael just mentioned that the bot, and then you can detect some misinformations, and then you can respond real quick. For example, it's just one. And then, is there any other ideas that you don't mind sharing with our students? Thank you.
Well, related to record linkage, so so as you point out, it increases the scalability. So for instance, it's going to make your life easier. If I had a suggestion, is you need to think about other data parallel tasks that we have, maybe specifically in econometrics or in causal inference. There are so many, and so you can think about each of these tasks as potentially the object of a package, right? That uses that technology, that uses GPU programming to speed up the process. So that was actually something kind of that was one of my goals, is to instill in you the will to write your own Python package using QPy, and learn CUDA, and for another, there are so many data parallel tasks. But in terms of, so I don't know, maybe Mike has more ideas, but so for instance, here the like you was talking about the project with Orange County. Here the benefit of this approach is, instead of taking a couple of days to get the results back, it just takes maybe a couple of hours, because they have so many voters. So it still takes quite some time, when you have 1.5, I don't know the exact number, but it's like in that ballpark, registered voters. So the number of comparisons you need to make is, you can imagine, quite large. But here you're just making our life easier. But really, once again, if you just open an econometrics textbook, you're going to be able to find 100 data parallel tasks, and each of these tasks is potentially a new package you can write. And I can be the only one writing packages, so please take a couple and write your own packages.
Yeah, I'd add just generally that in some ways I'm super jealous of you all, and I'm super jealous of Jacob, because we are at a point in time where I think, I've been at CalTech for 32 years, and I've been studying political science for 35 years. And we are at a real tipping point, I think, methodologically. We have access to unbelievable data that we have never had before. And we have access to unbelievable computing resources that we have never had before. If I was in my office, I would go to the shelf and pull down a computer tape. Now, Carl's probably old enough to remember computer tapes, but I don't think anybody else on the call probably
the mainframe.
Right? Yeah, the mainframe. Yeah, you'd be able to put an entire NES data set, 2,000 observations on a computer tape. Okay, now the phones that you carry around in your pocket have just hundreds or thousands of orders of magnitude larger amounts of storage space. So, so the applications we have, I think, are endless. All of the social media platforms that people are using today, I think, are ripe for study. We have done some work with data from, say, Twitter and Facebook, but there's very little study right now of platforms like Truth Social, Telegram, WhatsApp, and it is possible to get data from those platforms. TikTok is another example, and what's really brilliant about trying to study TikTok, of course, is that those of you who are on the platform know that the posts on TikTok, they're not simple like X posts where they're mainly text. They're multimodal. They have text, they have audio, and they have moving images. And so the computer vision problem there of analyzing multimodal data to extract or reduce the dimensionality of the information that is in a TikTok post is an incredibly interesting problem, and it really hasn't been well tackled yet, even by the computer scientists. So I just think that we're at this point where there's just so many amazing problems that students can face, and I do encourage them to take Jacob's advice. Learn Python, learn CUDA, learn how to use these tools, because if you train yourself to learn how to use these tools, you can do amazing research. And if you decide not to be an academic, like Jacob, you can get an incredible job in industry. And it's just a matter of learning these tools. And like I said, I'm just super jealous of grad students these days.
Mhm.
Yeah. Thank you. Yeah.
Thank you. This is you basically answer my question. I want to ask how much, because you are setting a forefront, a frontier of the computational social science, or maybe really doing charting the uncharted areas. And now give us a little more advice, and because we have a program called Social Data Analytics and Research, which is basically teaching social scientists to study big data, social data, and you just Mike and Jacob just taught us how to use GPUs. So how would you recommend in terms of pedagogy and also the curriculum change? We've been using teaching or based on R Studio R, and I teach SQL and some NoSQL. So give us any directions that we should incorporate in our teaching and maybe research in future. Yeah.
Mm-hmm. Jacob, you want to start?
Well, I would recommend. I think RStudio is great. I would recommend being familiar with like Jupyter notebooks and Visual Code as well. GitHub. I'm still not good at it. Suleika I saw that she joined. She can testify that I'm still not great at GitHub when I compare myself to what she does. But it's a discipline that you need to learn. And like when you're in grad school is the time to develop that discipline. Mike, if you want to add anything.
I think I would just confirm what Jacob said. Again, it's RStudio is great, but I will tell you that probably RStudio is going to be, for this generation of grad students, deprecated pretty quickly. And it's going to move towards Python and other programming languages like CUDA. So I would stay fresh and be ready to learn new languages that come forward. But again, doing collaborative work is very important today. So really learning how to use GitHub, I think, is super important. Techniques like we talked about today, working with different kinds of disparate data sets, trying to link them together, I think are really important tools to teach. But one thing I'd also say, to kind of go back to the earlier conversation we were having, is one bug that Jacob knows that I have in my bonnet is making sure that front and center in all curriculum of data science today is ethics. The ethical issues that, again, when I was in graduate school, were trivial. We very rarely had access to data with PII. In today's world, the ethical issues that we face dealing with data are vastly different and very complicated. And when I teach the data science class to our second-year graduate students in our program, I start with 2 weeks of ethics. We spend 20% of the class on the ethics of data science. And I start with it because I think it's so important. A lot of people will relegate ethics to the end of the class, or they'll put it at the end of a textbook. I really strongly encourage a focus on ethics and making sure that ethics is embedded throughout whatever curriculum you develop.
We have received. Yeah, indeed. Now,
and maybe another something slightly related that I was just thinking about. Actually, it's not related, but because I think we put a lot of emphasis on the technical side, and it's extremely important. But also, I think and I've taken machine learning classes, and sometimes the domain knowledge, or actually going through the process of thinking. So, for instance, you want to do a regression, thinking about what variables am I going to put in the regression. It's like in those classes, it's always an afterthought. But like the moment you go out in the world, that's all that matters. Because we all know all the different classification algorithms, regression algorithms, but whether you're going to do a good job is being able to take your dominant knowledge, so gain an understanding of the situation, what you're trying to predict, and come up with the variables. And like I feel, having been through my training very recently, I felt that was, at least especially in computer science, like most of the time just an afterthought, and you're kind of just expected to figure it out on your own, but you're not told that this how important it is. So I would emphasize that actually it's so critical, and I wish people were more vocal about that.
Great, yeah. I think it's a really, really important concluding remark, and also concluding our season of the colloquium. And yeah, and looks like we have new topics, and I want to bring you guys back and for the next season, or maybe in future events. Okay, Glenn, you have one more question, do you? Or remarks?
No,
Glenn?
sorry, just hit the wrong button.
Okay, all right, don't worry. Now, let me check on the on Taiwan side. So I hope the audience there, faculty and students, benefits great time, enjoy this colloquium event as much as I do. Yeah. So
Yes,
do we have any questions or comments and suggestions?
No, well, good. Yeah, and then so insightful, and then it's really, like you said, this is frontier, and then kind of eye-opening. But it takes, a lot of learning. We hope that the learning is not so steep that so everyone can try to get used to it. And so that's my comment. And I'll encourage my students to try to catch up, and so that open. It's kind of like an open door right there, and then we hope to explore more. Thank you very much. Yeah.
All right. I think we had a great night, and I want to say thank you again, Jacob and to Mike, and thank you for the great presentation and also the very insightful remarks. And kind of like I think I have some ideas I need to incorporate in my teaching next semester, and as I said before, I really hope we can invite you for our next events and maybe seminars, conferences, and I think hopefully we will make it happen soon. So I will keep in touch with both of you and work with Peter for that next event. All right, and I want to say thank you again. Thank you to all the attendees and for a great night and also a great morning. And
Yes.
all right, Peter.
Yeah. And then thank you for joining us for this season finale, if I may. So please do come back next season. And then let's looking forward to it. Thank you very much.
Yeah, check our website and also our YouTube channels. Yeah.
Yes.
All right.
All right.
Thank you again, Mike.
All right. Thank you.
Thank you, Jacob.
Thank you so much.
Good night.
Thank you very much.
Good night.
Yeah. Thank you,
Bye
Jacob.
all.
Thank you. Bye.
Thank you.
Thank you.
Mm.